Okay, it's 8:30, so let's go ahead and get started today. Hi, good morning, everybody. How's everybody doing on this fine morning? Doing good? Doing good? Yeah, it's cloudy, which is nice. I'm hoping we can get more cooler weather because I'm kind of sick of the heat a little bit. Okay, so the plan for today, I think we had a little bit of the last example that we have to finish up from last time, and then we're starting a whole new unit. So actually, we're going to say goodbye to control volume analysis for now, at least until the midterm, and then we're going to move on to kind of the next big part. So I should have mentioned this kind of before we started this whole unit, but like this period of this class, kind of in between the first midterm and the second one, I consider this to be kind of the big, this is kind of the almost like the meat and potatoes of fluid mechanics. So there's we're going to go over two types of analysis. So we're basically done with control volumes. So that's kind of the big first part. And then after that, we're going to go over differential analysis, which is kind of a different almost mindset on how to perform fluid analysis, where instead of performing integrals, we haven't really been performing integrals. We've kind of just been evaluating the expression. But instead of looking at control volumes, we're going to look more kind of use derivatives and to get more spatial information on the velocity field. So I'll go over that a little bit more once we get there. But before we start, are there any questions I can answer before that? Okay. So let's go ahead and finish up the example that we started last time. Okay. So I believe the example was we were looking at a fan. Okay. And so our fan looks something like this. Okay. And then the fan was blowing air this way. Okay. Right. So just like every control volume problem, we're going to start with drawing the actual control volume. Okay. So in this case, I'm going to use something that looks like this. Okay. And let's write out what we know about the inlet and the outlet. So we call this area 1. So this is going to be our inflow. Okay. And so we can say that the pressure upstream is going to be 0. So we say P1 is equal to 0. Okay. And the other thing we're going to assume is that the inlet area is very, very large. So we can say that A1 very large. Okay. Right. Like if you can imagine, like if you have like a standing fan or a fan in your room, the air behind the fan, you don't really feel it moving all that much. It has to be moving because there has to be a mass flow. But if you kind of stand far enough away from the fan, it's almost as if the air is still. Okay. But in order to kind of satisfy conservation of mass in this case, in order to have a inlet velocity at 0, we have to have the inlet area be really, really large. Okay. And if you remember from our discussion from hydrostatics, whenever we say something's really, really large, mathematically we take it to be almost like it's infinity, but it's not really infinity. It's just way larger than anything else in the problem. So so most of the times, we have to kind of get around this in the problem set. Okay. Okay, and so let's look at the outlet. So the outlet, we have a diameter. So we can say that D2 is equal to 0.6 meters. Okay. P2 is going to be 0, and U2 is going to be 12 meters per second. Okay. Okay. And since this is a conservation of energy problem, we also know how much work the fan is doing or how much power, say the fan is drawing from your electrical outlets. Okay. And so in terms of power, which we can denote that by work dot shaft, okay, our W dot shaft is going to be 0.4 kilowatts. Okay. And the other thing that we know is the density of air in this case, we're going to use 1.23 kilograms per meter cubed. Okay. Okay. And so if you recall from last time, we started this example after we discussed what was called the extended Bernoulli equation. And so the extended Bernoulli, was basically just like our old Bernoulli, but it had some additional terms to account for work and to account for what we called losses. Okay, so let me write out the expression. Okay, so we have P out over rho. Okay, remember the difference between P with the ponytail, which is pressure, and P without the ponytail, which is density. Okay. Okay, and we had our velocity term. Then we had our potential energy term. Okay, so those are our three amigos for Bernoulli. Okay. And then we had the same terms for the inlet. Okay, so that was usual Bernoulli. Okay, but our extended Bernoulli, remember, we added these additional terms. So we had an additional term to include any shaft work. Okay, so that's W dot shaft. Okay, and then we also had a term for any losses. Okay. Okay. And remember, these guys came out directly as a result of applying our control volume conservation of energy to a control volume. Okay? And so in this problem, what we're going to do is we're going to use this extended Bernoulli, and we're going to solve for one, what the losses are. Okay. So how much energy we're losing, you know, in this fan due to viscous dissipation. Okay. And the other thing we're going to solve for is the fan's efficiency. Okay, so how efficient is the fan, you know, in taking its input power and then converting that into actual fluid mechanical stuff. Okay. Okay. Any questions on the problem setup? So the question is, what did we apply to get the last two terms? So that was, yeah, so that was from the last lecture. So what we did basically was we took our control volume form of conservation of energy. Okay, so we took our RTT, applied it to energy, and then what we did was we connected it to Bernoulli equations. So you know, once we connected to Bernoulli, you know, we were able to make kind of a one-to-one connection with a lot of these terms. Normally, all of these guys. Okay. But what we had left after that was we had W dot shaft. Okay. So that was, you know, that comes directly from our RTT for conservation of energy. Okay. And then, you know, the other thing that we noticed was that, hey, you know, we hadn't assumed, you know, there's no viscosity. Because remember, when in our original Bernoulli, that was one of the assumptions that we had to make. And so in control volume, you know, we let up that assumption. And so once we let that up, we can say that, you know, if we introduce viscosity, the way that gets introduced into the energy equation is that it produces losses in energy. So very similar to friction, right? So we said that viscosity had the same effect on fluids as friction has on kind of solid objects like that. Yeah. Mm-hmm. Okay. And so let's now apply this extended Bernoulli to this equation. Okay. And so we have one inlet and we have one outlet. Okay. And so our inlet is on the left at 1. And so let's go ahead and start canceling out terms. Okay. And so since we know that P1 is equal to 0, you know, we can already cancel out the pressure in term. Okay. We also know that the velocity at the inlet, U1, is equal to 0, so we can cross that out. Okay. And then also, just by kind of looking at the figure, we can say that the height of the inlet is going to be the same as the height of the outlet, right? Because we're just moving horizontally here. So, you know, we're going to just cancel out those two terms there. Okay. Okay. And so that's at the inlet. And now let's apply the same thing at the outlet. So at the outlet, you know, we can only cancel out one term, which is the pressure. So since we know that P2 is equal to 0, we can just cancel out P out right there. Okay. And so all we're left with is U out squared is equal to W dot shaft minus the losses. And so what we can do is we can rearrange this expression to solve for the losses, because we know U out, we got that from the problem, and we know W dot shaft is going to be 0.4 kilowatts. So all we got to do is just plug in and solve for the losses. Okay. Okay. Any questions on this before I turn the page? Okay. Okay, so then if we do that, we get the following. We say that our losses is going to be equal to W dot shaft minus U out squared divided by 2. Okay. We plug in all the numbers. And then, oh, right. Okay. Before we do that, we need to do a little bit of conversion. Okay. And so, you know, the W dot shaft in this case is given in terms of power, right? So power is joules over second. Okay. But if you remember from when we did our extended Bernoulli, you know, this W dot shaft is supposed to have some other units. Okay. And so if you remember from our extend Bernoulli, you know, we had the strange units for this W dot shaft, and it had to be in joules per kilogram. Okay. Okay. And so the way that we obtain W dot shaft in joules per kilogram is that we can take our power. Okay. Okay. And our power is you know, given in units of joules per second. And then the way that we convert that is we divide it by m dot. Okay, so m dot is our mass flow rate. Okay. And the way that we obtain m dot is that we just simply compute the mass flow rate at the outlet. So m dot is just going to be rho a out, u out. Okay. And so this is going to be rho pi d out squared divided by 4. Okay. And so if we plug in the numbers for m dot, we got 4.17 kilograms per second. Okay. And so if we compute W dot shaft from this, we have 0.4 kilowatts, which is going to just be 400 watts, okay, divided by 4.17 kilograms per second. Okay. And then what we get is 95.85 joules per kilogram. Okay. And so now we can take this 95.85 joules per kilogram and plug it into W dot shaft. Okay. So that's a subtle thing. So remember, you know, if you're applying extended Bernoulli, you know, you have to convert the power into joules per kilogram. So you can't just use joules per second. So you have to take watts and you have to divide it by the mass flow rate in order to get joules per kilogram. Okay. Okay. And so we plug that into our expression up above, and we get losses is equal to 95.85 joules per kilogram. Okay. And then we're going to subtract the outlet velocity, so it's 12 meters per second squared divided by 2, and then what we get is 23.85 joules per kilogram. Okay. All right. Any questions on that? Okay.
Yeah, just
oh, sure.
Just wanted to clarify. Is it because of the joules that we're able to combine the meters per second squared?
So remember, m dot is mass flow rate. So mass flow rate is kilograms per second. And so if we divide joules per second divided by kilograms per second, the seconds are going to cancel out and we get joules over kilograms. Yeah. So it looks like this basically. So this expression right here is actually 400 joules per second, right? Because that's what watts is. So we do 400 joules per second divided by kilograms per second. The seconds cancel out and we get joules per kilogram. Okay. You got it?
I think so.
Okay. Okay. And so now let's solve for the efficiency. Okay. And so efficiency, you know, efficiency is kind of a very broad term that's used kind of way too much. But basically, the way that we define efficiency in this case is the percentage of input power that actually goes into performing useful work. Okay. And the way that we define useful work is anything that's not losses. So remember, losses are called losses because they're energy that's kind of lost to the ether, I guess you can say. I mean, it gets dissipated as heat, but once you lose energy and heat, it's very hard to get it back. Okay. And so the way that we define efficiency is like this. We give it the symbol eta, like this. Okay. And so we compute it by taking our W dot shaft, which is our input power, and we subtract the loss from it. Okay. And then we divide by the input power again. Okay, so this gives us the percentage. And so that you can think of the top as the amount of useful energy that we're getting out. So it's the input power minus the losses, and then we're dividing that by the total amount of power, that we're plugging in. Okay, and so if we plug in the numbers for this particular problem, we have 95.85 minus what we just computed, 23.85 divided by 95.85. Okay, and then what we get is 0.752. Okay, and so this fan, as it's currently constructed, has an efficiency of 75.2%. And so we lose about almost 25, almost a quarter of our power due to viscous losses in this system. Okay. All right. Any questions on that? Okay, so that basically closes our chapter on control volume analysis. So what we covered at the end right here was our extended Bernoulli. So extended Bernoulli, you might find it a little bit easier to work with than our usual RTT, because we've seen Bernoulli before, and it's kind of just an algebraic expression. And so if you come across a situation where you need conservation of energy, extended Bernoulli is a good option for you. The only thing that you have to be careful of when using extended Bernoulli is that you have to convert any power terms into joules per kilogram. So you have to divide by the mass flow rate. So that's the one thing that you have to remember when you're using extended Bernoulli. Okay. Okay. So that's control volume analysis. So we've been doing that for a while, and so now we're kind of ready to move on to something else. Okay? And so we're going to spend the next 2 weeks covering what I call differential flow analysis, or fluid analysis with derivatives and differential equations. Okay? Because with control volume analysis, our central tool was Reynolds transport theorem. Okay? And the thing about Reynolds transport theorem was that it was an integral expression. So we had a bunch of integrals that were equal to each other, okay? Or that we're adding them together and we're setting them equal. And that was kind of the central thing. And so the thing with integrals is that, integrals are great in that they kind of let you see something from like a total, as like almost like an average from like a total view. Okay. And so, one analogy that I like to think of is that, say, you're baking, a bunch of cookies, right? And so say that you baked a tray of, say, like 24 cookies, right? And so you pull them out of the oven. And so the way that you would view this from like a control volume analysis or with integrals is that you would just look at the whole batch of cookies just from far away and just say that, yeah, that's a good batch of cookies. Okay? But there's another way that you can judge a batch of cookies, right? So you can take each individual one and you can look at the cookie and say, this one's a little bit deformed, this one, not enough chocolate chips in this one has too many chocolate chips, right? And so that's kind of what differential fluid analysis is. So with differential fluid analysis, we're really going to get into, the details of, how things vary. Okay. And so if I could sum it up in kind of a, in a nutshell, what we're going to learn at differential fluid analysis is how can we analyze, you know, this, how velocity and pressure vary in space and time? Okay. So in other words, what we're going to be solving for is we're going to be solving for the velocity and pressure fields. Okay. Okay. So it's a very different, you know, kind of a very different mindset on you know, how to solve for these. So it's you know, it's not quite Lagrangian. So I think that's, you know, the thing that everyone kind of you know, assumes is that, you know, differential fluid analysis is like Lagrangian. It's not Lagrangian. So we're still going to be in the Eulerian point of view, because, you know, we're not going to be looking at individual particles, you know, but we are going to be interested in saying, you know, how do our quantities actually vary in space? Okay. And so I have one image to kind of illustrate this. Okay. And so in control volumes, you know, say that we have, you know, a flow in a pipe like this. Okay. And, you know, say that we want to compute like the mass flow rate here. Okay. And so remember, our mass flow rate is given by the product of the density times the area times the velocity. Okay. And what we kind of implicitly assumed here is that our velocity was uniform across this entire plane. Right? And so if we call this like U naught right here, you know, then we say that the fluid velocity across this entire, you know, cross section was the same. Okay? Or in other words, you know, we had a uniform velocity profile. Okay? Which was really convenient because, you know, we didn't have to actually perform any integrals. You know, we can just multiply things straight out. Okay. But in reality, it's actually not like this. So actually, you know, say if you have a pipe like this, okay, and we can draw the velocity profile or the velocity fields, you know, in reality, it actually looks something like this. Okay. And so let's say that, you know, we have the y direction going up this way. Okay. And so we're going to have u as a function of y. Okay. And so this is a very famous parabolic velocity profile. And so right now, with the tools that we have equipped with control volumes and Reynolds transport, you know, we're not equipped to analyze something like this, to say, you know, how does the fluid velocity change as a function of space? Okay? The only thing we can do is we can kind of just look at systems and control volumes as a whole, you know, which is really valuable for a lot of situations. But there might be some situations which call for the type on the right, where we want to solve for, you know, we really want to solve for like a detailed map or a detailed, you know, description of how velocity and pressure vary in a fluid. Okay. And so this is especially important for, you know, applications that involve drag or shear stresses. Okay. And so we'll actually see later on, you know, how does, you know, the velocity and pressure fields contribute to a drag force, you know, which is extremely important if you're going to be designing cars or airplanes. You know, drag is something that you need to know really well. Okay. And so the tools that we're going to need to do this is it's going to be a whole different set of tools, where instead of integrals, we're going to be doing a lot of derivatives and eventually some differential equations. And so, you know, if you're taking 308 right now, that's great. But if you've taken in the past, now is the time to maybe dust off some of your notes, or maybe your notes from Math 258, because we're going to be making really good use of it. Okay. All right. Any questions on this so far? All right, so eventually, we're going to be working our way towards something called the Navier-Stokes equations. Okay, and so we're not going to do it this week, but we'll probably next week. And so Navier-Stokes is probably as close as you can get to like a master equation for fluid mechanics. Okay? And so that's very rare. So I think in a lot of disciplines there's no master equations that can kind of solve for anything. But Navier-Stokes is probably one of the closest that you can get. So if you can solve Navier-Stokes, first of all, you would get $1 million because no one's been able to solve Navier-Stokes, at least in a general sense. It's one of those unsolvable problems that's still out there in mathematics right now, which is fascinating. But we can solve Navier-Stokes in some kind of limited situations. And what you'll see is that you can get basically almost anything that you would want from fluid mechanics from the Navier-Stokes. So that's something to look forward to. Okay? I love Navier-Stokes. I named my Wi-Fi after Navier-Stokes here in my apartment. Okay, so before we do that, we need to revisit kinematics just a little bit. Okay. So I know we already had a whole week on fluid kinematics, but we didn't see the whole story, mostly just because back then I wanted to keep things mostly relevant to control volume analysis. So we're gonna come back to it a little bit here. Okay, so let's start with, remember what we call the material derivative. Okay, and so in particular, let's look at the acceleration field, which we obtained by taking the material derivative of velocity. So we can say that acceleration with a vector is equal to big D U dt. Remember, our material derivative had two terms. So we had one term for the time derivative. So we have partial u, partial t. Okay? And then it had all of the convective terms. So we had u, partial x, plus v, partial u, partial y, plus w, partial u, partial z. Okay? And remember, the way that we described these terms were the following. So we had this guy, which was our unsteady term. Okay. And then these guys, which was our spatial or convective variation. Okay. Because remember that we said that things can vary either in time or in space for fluids. Okay. And so that was the material derivative. So that's going to be a big part. So you'll actually see this again. This is actually a big part of the Navier-Stokes equations. Okay. So I just wanted to kind of remind you of that as we start going. But let's talk a bit more about fluid deformation. Because we haven't really talked about yet, we've stated how fluid can flow, but flow, as you know, is kind of a very, very complex motion, right? So if you look at fluid flow in a river or fluid flow out of your coffee machine, it's actually a very, very complex phenomenon. It's not like it's not all the fluids are going in a straight line like this. Some are going faster than the other ones. Some are you can have swirling and all that stuff. You can have whirlpools. So let's talk a little bit about how fluids can deform. Okay, and so for all these figures here, I'm going to draw kind of a square. Okay, and so you can kind of think of a square as kind of the starting starting position for that for a fluid. Okay, and then from that square, I'm going to draw kind of dotted lines to kind of tell you how does the fluid deform. And so I've set up kind of a equality here. And so on the left-hand side, we're going to say that this is going to be just general motion. Okay. And so this is kind of a general, way that fluids can deform. Okay? And so fluid deformation, can be thought of as like this. So, if you have just a parcel of fluid that's given by the square, it can deform in lots of different ways. So, I'm just going to draw kind of a generic thing. It looks like that, okay? And so this is kind of, this general motion kind of encapsulates all the different ways that fluid can deform, okay? And then what I'm saying with this equal sign is that, we can break up this general motion into, 4 different modes, okay? Okay, and so the first one that we're gonna go over is called translation. Okay, and so, just like a solid block, a fluid can just simply translate, okay? Right? And so the next thing that we can do is linear deformation. Okay. And so the next thing that we'll cover is rotation. And so the last thing that we'll cover is angular deformation. Okay. And so we can say that, general fluid motion can be thought of as, the sum of all these different things. Okay. And so let's look at translation first. So translation is simply just that you take an object, you take, like, say, this phone right here, and then you just move it to a different location. So it retains its same size and retains its same shape. It just moves just linearly to a different location. Okay. And so the way that we can visually depict this is by, if we draw the exact same square, just in a different location. Okay. And so this is simply translation. So translation, we start with the black box, and then we move the black box to another location. Okay. So you can see that the red box there, as close as I could get it, looks exactly the same as the black box. It's just in a different location. Okay, so that's translation. And so another mode of deformation, another mode is going to be linear deformation. Okay. And so linear deformation, another way that we can think about it as just simply expansion and contraction, okay? And so you can see what I've drawn from the red box here is that our starting black box just got bigger than before, okay? And so that's linear deformation. So linear deformation, we retain generally the same shape, it just gets bigger or small, okay? So it's just expansion or contraction. Rotation is pretty self-explanatory. So it's rotation, we're going to take our box and just simply rotate it. Okay. Right. So it should, for rotation, we're not changing any volume or anything like that. We're just kind of rotating it to a different orientation. Okay. Okay. And so the last one that we'll go over is angular deformation. Okay. So angular deformation is kind of the most interesting one because that's the only one where, which can cause the box to change shape. Extremely hard because it's at the edge of my iPad, but you can kind of see. So in angular deformation, the sides of our square are kind of getting either the angle between the sides are either getting smaller or bigger, and that's what causes the fluid element to change shape. Okay. Okay. And so if we break down fluid deformation into these 4 different modes, then this can kind of help us explain how velocity fields and pressure fields actually come about. Okay. All right. Any questions on this? Okay. Yeah. So we have these 4 modes of fluid. So you can kind of almost think of these as kind of 4 different ways that a fluid can deform, and when you add them all together and you combine them, then you get kind of general fluid motion. Okay, so that's kind of. And so what we're going to do from here is that we're going to kind of group these together in a little bit. Okay. And so what we can kind of say is that translation and linear deformation, the mathematics for this are going to be kind of the same. Okay. And so what we're going to do is we're going to come up with a mathematical operator that kind of summarizes translation and linear deformation. Actually, mostly just linear deformation. Okay. And then another thing that we're going to do is we're going to use a different mathematical operator to describe rotation or angular deformation. Okay. Okay. So let's go ahead and jump into that. All right. So let's start with linear motion and deformation. Okay. Okay. And so the reason we call these linear deformations is that, these only involve just simple translations or expansions, contractions. And so there's no change, there's no rotation and no change in shape. Okay. And so the mathematical expression like this will be the following. Okay. And so, mathematically, what we're really interested in is what's called the relative rate of volume change. Okay. And so what we want is a mathematical expression for the relative rate of volume change. Okay. And so the mathematical form of this, if everyone teaches 308 a little bit differently, but you might have heard this operator called the divergence. Okay. And so mathematically it looks like this. And so we have this symbol right here, this upside down triangle. If you've never seen this expression, if you've never seen this symbol before, it's called a nabla. Okay. And the way that you compute that is the following. So remember, this u vector right here is our velocity vector. So it has x, y, and z components. Okay. And so the way that we compute the divergence is.
Professor, I think you might have some internet issues. Did he just
yeah, yeah. So I forgot that it mutes me when I come back from disconnection. So are we all back?
It was really laggy.
Okay. So let me go back a page just to so did everyone get this last page over here with all the translation, linear deformation, rotation, angular deformation? Everyone get this this part here? Okay. Okay. And so what I want to do now is I want to take kind of those 4 different modes and we kind of group them together. So I group kind of these first 2 for translation and linear deformation. Okay. And then what we want to do is we want to kind of form a mathematical expression for this. Okay? And so the first we're going to do is translation and linear deformation. And so the mathematical operator that we're going to use is called the divergence. So who's seen the divergence before in a previous class? So probably 308 you might have seen it, but you might have seen it in a previous math class too. Okay, that's okay. We're going to go over the divergence. So the way that we denote the divergence is by this. Okay, and so it's a dot product between 2 different things. So first we have this upside down triangle symbol here, which is called a nabla. And then we dot product that with our velocity vector. Okay. And so if you write out, the whole thing, we get the following. So it's simply just a sum of the partial derivatives of each of the different expressions. So remember, our u vector here has x, y, z components, and so we're going to take the x derivative of the x component of velocity, so du dx, and then we take the y derivative of the y component of velocity. And then we take the z component of the z derivative of the z component of velocity. Okay? So as du dx plus dv dy plus dw dz. Okay? Right. And so this is going to be important later because we're going to form basically conservation of mass with derivatives. Okay. Okay. Okay, so that's our mathematical operator for all the linear modes of motion. Okay, so we're gonna use the divergence for that. Okay, and so for angular motion and deformation, these describe a fluid's tendency to rotate or swirl. Okay. And so the way that the mathematical tool that we're going to use to describe this is called the curl. So who's heard of the curl before from a previous math class? Okay, yeah. Hopefully it at least sounds familiar. So you don't have to remember exactly how to compute it or whatever, but at least people are familiar with it, which is all that you can ask for, right? Okay. And so the way that we're going to quantify, swirling and rotating in a fluid is we're just going to take the curl of the velocity field. Right? So we're going to take our velocity vector and just take the curl of that, and then that's going to be, how we quantify that. Okay. Okay. Any questions on this page before we write out the curl? Okay. Okay. And so the curl is given by the following. So we're going to use our same nabla. Okay. So nabla, it's used a lot in fluid mechanics. And so, the way that we compute the curls, we take instead of the dot product, we take the cross product between nabla and our velocity. Okay. And so if you remember, there's lots of different ways to compute cross products. This is the one that that I remember the easiest. Okay. And so you kind of form this 3x3 matrix right here. Okay. So on the top row you have I, j, and k, which are our unit vectors in the x, y, and z directions. Okay. And the next row you have all your partial derivatives. So we have partial derivative with respect to x, partial derivative with respect to y, and partial derivative with respect to z. Okay. And on the bottom row, you have our velocity components. So we have u, v, and w. Okay. Right. And then so to actually compute the curl, what you need to do is you need to take the determinant of this guy. Okay. Okay. And then after you take the determinant, what you get from this expression is a vector, right? Right. And so remember, if you take the cross product between two vectors, you get a vector back. Okay. And actually, from the previous page, when we took the divergence, for the divergence, we took a dot product, right? And so if you remember, the result of a dot product between two vectors is a scalar, right? And so even though we have this complicated expression right here for the divergence, because we're just simply adding them all together, we get just a scalar number out of this. We just get some number. Okay. So remember, a dot product you get a number, and then for a cross product you get a vector. Okay. And so this is actually a really important quantity for fluids, especially if you're going to get into like aerospace and you're talking about turbulence a lot. Okay. And so I'm really bad at drawing this symbol right here. So the symbol is called zeta. Okay. But when I draw it, it just looks like a tornado. So I just simply call this tornado all the time. Okay. And it's simply just going to be equal to the curl. Okay. And then what this tornado symbol is called is this is called a vorticity. Okay. And so it gets that you can kind of tell it gets that name because it's talking about vortexes. Okay. And so we're going to talk about a very special case, for fluids later, where if you have the cross product of these two, or you have the, the curl of the velocity field equal to 0, and of course this is a 0 vector, so all the components are 0, then what we say for that flow is that it's irrotation. Okay, and so a fluid where the curl is 0 means that the fluid is irrotation. Okay. Okay. Any questions on this?
Yeah, so your tornado is the vorticity?
Yes. Right? Yeah. Yeah. So the actual Greek symbol for that is called zeta, but I'm really bad at drawing zeta, so I just call it tornado. And I think it's a little bit it's a little bit easier to remember for me like that, because tornadoes like to swirl around, so that's the same expression for vorticity. So vorticity is not exactly rotation, but it's a way that you can kind of quantify rotation. And so if something is kind of swirling around like a whirlpool, and you have two different whirlpools and you want to compare them to the other one, right? And so the way that you can compare them is you can compare the vorticities between them. So it's kind of like the same way that we use velocity to kind of quantify speed or quantify how fast something's moving. Vorticity is kind of a way that we quantify how much it's rotating. Yeah. Mm-hmm. All right. Okay, so those are kind of the mathematical tools. So that was kind of a crash course a little bit in kinematics. So from kinematics, remember, I want you to remember what the material derivative is, how we express it mathematically. I want you to know what the divergence is, and what it represents in a fluid. And I also want you to know what is the curl, what exactly is the curl, and what does that represent for a fluid as well. Okay? So now we're ready to kind of get back to what we were doing for the past couple of weeks, which is our conservation laws. Okay, so let's start with conservation of mass. Okay. And so our starting point, eventually what we want is we want a differential equation that describes conservation of mass. Okay? Because that's the whole theme of this week, which is differential fluid analysis. Okay. And so to get that, let's start actually with our integral form for conservation of mass. So we're going to start with RTT. Okay. So just to kind of refresh your memory, here's our RTT expression for conservation of mass. And so we take the partial time derivative of rho dV, okay, over the control volume, plus our inflow outflow term. So we have integral of the control surface of rho carrying velocity. And so that's U dot N, okay, dA. And all this is equal to 0. Okay. Right? And so in order to get a differential equation, we're going to take this and we're going to apply it to a really, really small control volume. Okay? And so the formal mathematical term for a really, really small something is called infinitesimally small. But it usually takes me several tries to say infinitesimally well. I'm 2 for 2 today, but that usually doesn't happen. And so, the way I usually say is that it's just really, really small. So it's like microscopic that you can think of it. Okay? And so, because we're doing something, something that it's extremely small, what we need to do is we need to take the limit of this. Okay? Okay? And so if we take the limit, what we get is the following. And so our first term, if we take a volume that's really, really small, we simply just get the time derivative of the density. Okay, so we have d rho dt, okay, plus the following. Okay, and so we have ddx of rho times u plus ddy of rho times v plus ddz of rho times w, and the sum of all these guys is equal to 0. And so just to kind of relate this back to RTT, this first term right here is an unsteady variation in density. Okay, and then this this next term is going to be the net rate of mass flow, because it came from our surface integral term. Okay, and so we have a different form for conservation of mass, but they represent the same things. Okay, and so in this limit where we take kind of a really small control volume, you can kind of see that we have obtained. We've obtained we've gone from an integral expression down here to a differential equation. Okay. And so this is the differential equation that that can be used to express conservation of mass for a general fluid. Okay. All right, so I know that going from the integral expression down to the differential one is a little bit hand wavy, but the details of that derivation are not so important. So I kind of want to focus more on how does this apply to fluid mechanics, and how we can actually use this to solve for problems. Okay. All right, so are there any questions on this before I turn the page? Sorry about the leaf blower.
It's not that loud. It's fine.
Okay, that's good. I guess it's louder on my side than for you guys. Okay, and so this expression right here it's fine. So actually we can apply this this differential equation here for any fluid. So that includes compressible flow, which is something that's really important. Okay. But remember, for this class, most of the time we assume the flow is incompressible, okay? Just for mathematical simplicity. Okay? And so for incompressible flows, we actually have a much simpler expression for conservation of mass. Okay. And so for incompressible flows, remember, the thing with incompressible flows is that the density is a constant, right? And so for the density is a constant, basically any derivative that involves density here is going to go away. Okay. And so if we do that, we are left with the following. Okay. And so all we're left with is du dx plus dv dy plus dw dz is equal to 0. Okay. Right? So this should look familiar for you because we literally just saw it like 10 minutes ago. And so this is the divergence of the velocity. Okay. And so for an incompressible fluid, in order for it to satisfy conservation of mass, then the divergence of that velocity field has to equal to 0. Okay. 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 And so this specific form of conservation of mass for an incompressible fluid, because it has this simple kind of mathematical expression, it has a special name. So sometimes we call this the continuity equation. Okay. And so just for completeness, sometimes you might have flows where it's more convenient to use cylindrical coordinates. Okay? And so this expression which we have at the top here is the continuity equation in Cartesian. Okay? But we can come up with the same expression for cylindrical coordinates. Okay? And so I'm not going to derive this, so I'm just going to give this to you. Okay? And you'll see why. Okay? And so we have 1 over r, partial r, of r times ur. Okay? And so ur right here is going to be the r component of velocity. Okay? Plus 1 over r partial theta of u theta. Okay? Plus partial z of u z. Okay? And all this is equal to 0. And so this is basically just the cylindrical coordinate form of our continuity equation. And remember, this is for incompressible fluids. Okay. All right. Any questions on this? Okay. Okay. And so that's conservation of mass. So actually we're not going to go on to momentum yet, because momentum is actually going to be Navier-Stokes. So we're gonna kind of stick around with this, and you'll see that there's kind of enough to handle with this. Okay? And so with this conservation of mass, we can actually use this to start solving for some problems. Okay? And so the way that we're going to do that is we're going to introduce something called a stream function. Okay. Right. Oh, sure. Mm-hmm. Right. You good? Yep. Okay. And so for stream functions, what we're going to do is we're going to focus just on 2D. Okay. Okay. Because what you'll see is that with 2D flows, it's already kind of complicated enough, and it's a lot easier to draw 2D flows on a 2D piece of paper than on a 3D flow. So technology, we haven't figured out how to be able to effectively draw in 3D yet, and so until then, we're going to focus on 2D flows. And so for 2D flows, our continuity equation simplifies quite a bit. Okay? And so we're just going to have 2 terms. Okay? And so we're just going to have du dx plus dv dy is equal to 0. Okay? And so in these situations, we can define a special function that relates the velocities. Okay? And the reason we're defining the special function is that the above equation is fine, but we're solving for 2 things. Okay? And when we're solving for 2 things in a differential equation, that's usually kind of a difficult thing to do. And so we're going to define this special function called psi. Okay? Okay? And we're going to express the velocities in terms of this function psi. Right? And so if we define our function psi to be like this, so we said that the x velocity is equal to d psi dy, and our y velocity would be negative d psi dx. Okay? And we can see that if we plug these guys into our expression up here, you can see that our continuity is going to be satisfied. Okay? And so, first let's take, this u right here and plug it in right there. Okay? And so we have d dx of u, which is d psi dy. Okay? And we have plus d dy. Use a different color for this. Okay. So we plug this in right here. Okay. And so we have d dy of d minus d psi dx. Okay. And you can see that these two terms are equal and opposite, and so that they equal 0. Okay. Okay. So why do we want to do this? Why do we want to introduce this new function psi? Right. And so it's nice because psi right here is actually going to be a scalar function. Okay. That means there's only going to be one psi, and so it's not like a vector, so it's not like it has its components. And so just by the fact that it's a scalar quantity means that it's going to be easier to solve for. Okay. And so instead of solving for separate u and v, we just have to solve for one psi, and that's okay. Okay. And then the other nice thing is that if you have constant psi, or in other words, lines in your flow field where psi is constant, okay, these are going to be our streamlines. And so if you recall, from a couple weeks ago, what streamlines are nothing more than just, lines that follow the flow. Okay. Oh. All right, so the question is, how do you spell psi? So psi is spelled like this. Okay, so PSI. Mm-hmm. Yeah, so it looks like kind of Poseidon's trident, but it's spelled PSI. All right, any questions on this? Okay. Okay, so that's what a stream function is. I just quickly want to go over what it looks like in cylindrical coordinates. Okay? And so there's a cylindrical coordinates version of this. Okay? And so the way that we get that, so say that we want the velocity component in the r direction. And so we have u sub r is equal to 1 over r d psi d theta. Okay? We also have u theta, which is going to be minus d psi dr. Okay? And so those are kind of the equivalents in cylindrical coordinates. Okay? Okay, so let's do an example just to show you, how these are used in action. Okay? And so let's say that we have a velocity field where the components are given by the following. And so let's say that our u velocity is given by 2 times y, and then v is given by 4 times x. Okay? Okay? And so from these velocity components, let's solve for the stream function psi. Okay? Okay, and so the way that we're going to solve for psi is that we're going to simply, integrate, these expressions right here. Okay? And so, one thing to note, before we move on, is that even though psi is a scalar quantity, it's going to depend on x and y. Okay. And so let's take our u velocity here. So our u velocity is going to be 2 times y. Okay. And then let's relate this to our psi expression. So from the previous page, we know that psi, or u, is equal to d psi dy. Okay. Okay. And so let's integrate this with respect to y. Okay. And then what we get is, and so if we integrate to y, then we get y squared. Okay. Okay. And since we just integrated in y, what we have to do is we have to add an additional function here, and our additional function is going to be a function of x, right? Because remember, since psi is a function of x and y, if we just simply integrate with y, we haven't taken account for x yet. So what we get from performing this first integral is that psi is equal to y squared plus f1 of x. Okay. And so now let's do the v components. We know that v is equal to 4x. Okay. Okay. And so v is going to be equal to minus d psi dx. Okay. And then same thing here, we're going to integrate. But now we're going to integrate with respect to x. Okay. And so from this, we get that psi is equal to minus 2x squared plus f2 of y. Okay. All right, so same thing here. So since we're just performing an integral with respect to x, we don't know what the y component is. Okay. And so since these have to be the same psi, then what we, even though we perform the integral in two different ways, this psi has to be the same as this psi. Okay? And so what we can say from this is that this y squared has to be our function f2 right here, right? Because f2 right here is only a function of y, right? And the only thing that that equates to this in the above is just going to be y squared. Okay. And then similarly, this function of x right here, so this f1x, the only thing that it possibly could be is minus 2x squared. Okay. Okay. And so if we equate these together, then we get that psi is equal to y squared minus 2x squared plus c. Okay. And so we have to add a plus c there because that's going to be our constant. Okay. And so that's our arbitrary constant for this expression. Okay. Because we've only been able to solve for all the x and y terms, but because we're still performing these indefinite integrals, we still have to have this this arbitrary constant out front. Okay. All right. Any questions on this? Okay. All right, so we've been doing a lot of just math today. So I kind of want to take just a small break from this. So, remember this, these velocity components, 2x, 2y, and 4x, these describe the actual velocity field, right? And so we can actually draw this, right? So we can say our velocity vector in this case is going to be 2y and 4x, okay? And so if you actually draw this in kind of the Cartesian plane, it looks like this, okay? And so let me draw lines that go like this. And so this is a very special flow in that it almost looks like flow that's coming in at kind of like a cross intersection like this. Okay. And so if you think of these kind of this x thing is kind of like a wall, okay, then the flow is going to go all around it. Okay. And so the flow field actually looks like this. And so you have velocity, you have fluid that's going to come into this corner and it's going to turn around. And the same, and it's going to look like this in all the other quadrants. Okay. Okay. Okay, and so this is kind of a visual depiction or a visual description of our velocity field. Okay, because remember, you know, the big difference now with differential fluid analysis is that we're more interested in these cases, right? So we're interested in, you know, what does the flow patterns look like? What does the pressure patterns look like, right? So we're interested in seeing, you know, the details of, you know, how does the flow actually, you know, look like in our domain. Okay? So that's very different from our control volume analysis, where we just looked at kind of a control volume as a whole, and we just kind of looked at the overall variables of like pressure and energy and momentum and things like that. So now we're getting into the details of, you know, what does the actual flow patterns look like? And this differential fluid analysis with the stream functions kind of gives us a way to actually do that. Okay. Okay. All right. And so now that we've kind of, you know, built up this this knowledge of the stream functions, we're now ready to get into what's called potential flow. And so potential flow is kind of a big area of fluid mechanics that can be used to describe, you know, that can be used to perform, you know, this very kind of analysis. Okay. And so our starting point for this is going to be our stream function. Okay. And so just from the definition of stream functions, we know that stream functions already satisfy conservation of mass. Okay. Okay. But let's impose kind of an additional constraint on the flow. Okay. Okay. And so let's also require that our flows that are defined by these stream functions are also going to be irrotational. Okay. And if you recall from the earlier parts of the lecture today, an irrotational flow means that the curl of the velocity is going to be equal to 0. Okay. Okay. And so let's write out what the curl is in 2D. So in 2D, it looks like this. Okay. So in other words, you know, we have this expression right here. Right. And so the curl in 2D is just dv dx minus du dy. Okay. And so, you know, let's take this expression and let's plug in our stream functions. Okay. Okay. And so first thing we have is dv dx. Okay. So dv dx is going to be d dx of v, where v is minus d psi dx. Okay. And from this, we're going to subtract d dy of u. Okay. So u is going to be d psi dx. Okay. And this is all equal to 0. Okay. And so if we perform, oh, d psi dy, sorry. Okay. And so if we perform these derivatives, then we get minus d squared psi dx squared minus d squared psi dy squared. Okay. This is equal to 0. Okay. And if we factor out a -1, just for computational convenience, we get the following. Okay. Okay. And so if we factor out the -1, then we get d squared psi dx squared plus d squared psi dy squared, and all that's equal to 0. Okay. This kind of a mathematical expression right here is actually a very famous one in partial differential equations. Okay. And so the name for this this partial differential equation right here is actually called Laplace's equation. Okay. And so Laplace's equation is actually a very famous partial differential equation. We're not going to actually solve it, But what we're actually going to do is we're going to take advantage of a lot of its nice properties to allow us to model some very complex fluid flow. Okay. Okay. Any final questions on this? Okay. So we're out of time for today, so that's 9:45. So I know today was a lot of kind of very dry mathematics, but hopefully by next time, next time what we're going to do is we're going to see how this is actually applied, and we can actually see some really nice flow patterns from this. Okay. So I know today was a little bit dry, but you know, kind of hang in there, and on Wednesday, you know, we'll pick this up and we'll see how this is actually applied. Okay. So thank you everybody for tuning in today. Hope everyone has a good rest of today, and I'll see you guys on Wednesday.
Thanks, Professor.
Thanks, Chris.
Enjoy your day.
Thanks, Dr. Chen. We'll see
Thanks, guys.
you later.
Yep, see you later.
Professor?
Yep. Mm-hmm.
I had a question.
Sure.
How do you know which way the streamline would go?
Yeah, so that's right. So that's a good question. So, you know, these, for this particular example, you know, the way that we can find these vectors is that we can just plug in values of x and y, right? And so let's just take a point right here. Okay? And so let's say that this location has the coordinates, you know, 2, 0. Okay? And so what we can do is we can plug these guys in to our expression up here. Okay? And so if we plug in 2 for x and 0 for y, then what we get is u is equal to 0, 8. Okay? And so 0, 8 is a vector that points up like that. Okay? And so all we have to do is just plug in values for x and y and then look and see which direction that vector goes. And that tells us which direction the flow is going to go.
Okay, thank you.
Yep. Mm-hmm.